Good afternoon. With your permission, I present a work, Helicopter's Turboshaft Engine's Intelligent Control Algorithm Synthesis, taken into account required quality provision. At the helicopter's turboshaft engine automatic control system operation mode, after solving the problem of ensuring stability, the problem arises of ensuring the required indicators of the quality of transit processes, overshoot, control time, and other. Often these requirements and contradictory, which is primarily due to peculiarities of the functioning of systems. One of the promising directions for the development of helicopters' turboshaft engine controls is the use of artificial intelligent components in their composition, production rules, fuzzy logic, artificial neural networks, hybrid neural-fuzzy architectures, genetic algorithms. Therefore, increasing the economic efficiency and maintaining a high level of reliability of the operation of helicopter's turboshaft engine at the stage of operation in condition of special operational situation based on the development of theoretical foundation methods and means of intelligent controls of its modes is an urgent scientific and applied task. Modern approach to the implementation of the main strategies for turboshaft engine development, operation on condition, and ensuring system safety involve the intellectualization of turboshaft engine all subsystems and information integration with the engine control, monitoring, and diagnostic system FADEC in order to reliably assess the state, identify failures, and ensure normal operation engine due to FADEC reconfiguration. It should be noted the hybrid systems for turboshaft engine operational status classifying and currently widespread with which are used in the structure of fuzzy logic paths and neural networks. Hybrid systems compare the actual turboshaft engine operational status in terms of vibration velocity and vibration acceleration with possible typical operational status that store the knowledge base of the system, which will make it possible to classify the current turboshaft engine operational status and predict its further changes. The disadvantage of hybrid system is need for a large amount of initial data for training and intelligent diagnostic system, as well the difficulty of monitoring the correctness of the diagnostics. This author's group developed a modified closed onboard helicopter's turboshaft automatic control system, which is supplemented with plug-in software modules that implement adaptive control methods, signal adaptation module, parametric adaptation module, linear model submodule, custom model submodule. Each block of the developed modified closed onboard helicopter's turboshaft engine automatic control system is implemented using neural network technologies, which have shown high efficiency and stability in the research of transient processes in the helicopter's turboshaft engine. However, the use of linear neural network did not solve the problem of overshooting the system. Therefore, this work proposes an alternative approach of intelligent description of the developed modified closed onboard helicopter's turboshaft engine automatic control system using neural-fuzzy modeling using hybrid neural-fuzzy networks, on the basis of which fuzzy inference systems are generated. According to the goal of the work, it is proposed to use the method of synthesis of automatic control system using hybrid neural-fuzzy networks. Hybrid neural-fuzzy networks combine the advantage of inference system and neural networks. On the one hand, they allow developing and presenting system models in the form of fuzzy production rules, which are visual and easy to interpret, and on the other hand, neural network methods are used to build fuzzy production rules, which is a more convenient and less time-consuming process for designers. The algorithm described and is used when constructing a hybrid neural fuzzy network, then implement decision-making of the choice of system parameters in order to satisfy the given overshot indicators. The choice is made according to several criteria: gain factors and time constants is non-holonomic cross-couplings. Figures show the structure of the fuzzy inference system under consideration. The location of the coordinating path in the block diagram of the multiply connected helicopter's turboshaft engine automatic control system shows in figure. In hybrid neural fuzzy network, logical conclusions are made using the fuzzy logic apparatus, and the corresponding membership function are tuned using the neural network training algorithm. Backpropagation error, that is, the description of the research object is performed by the fuzzy logic methods, and the tuning this model by artificial neural network methods to obtain a more accurate correspondence to the considered model of the helicopter's turboshaft engine. The main subsystem is a fuzzy inference system with output variable of a discrete type. The fuzzy inference system aggregates with the neural networks. As a result, a hybrid neural fuzzy network of the NFIS type is obtained, the adjustable parameters of which are the membership function parameters. Hybrid neural fuzzy network block diagram is shown in figure. Units function analogous of neurons is a convolutional neural network of the hybrid neural fuzzy network block diagram shown in figure are reflected in table. In the experimental work, the input signal obtained according to previous equation is used and analyzed for the TV3117 turboshaft engine, which is part of a power plant of the Mi-8 MTV helicopter according to the data obtained on board the helicopter during the flight. This slide shows the results of input signal preprocessing. After the randomization procedure, the actual training control and test samples were selected. Is a ratio of 2:1, that is 67% and 33%. The distance between the classes practically coincide in each of the considered samples, therefore the training and test samples are representative. As a result of experiments of the development of the hybrid neural fuzzy network structure, the diagrams was obtained shows in figure, where layer 1, 3 input variables, the parameters of which unequally determine the helicopter's turboshaft engine thermogas dynamic parameters values. Layer 2, 3 terms for each automatic control system input. Layer 3, 3 rules of fuzzy knowledge base. Layer 4, the 3 classes of the output variable. Layer 5, the results is defuzzified. As a result of training the developed hybrid neural fuzzy network, according to the algorithm described above, an object model was obtained with membership functions, parameters, and weights of fuzzy rules, which are given in table. As a result of modeling the dynamics of changes in helicopter's turboshaft engine thermogas dynamic parameters according to the training sample, depending on the model time, the obtained results are present in figure. Other figures show the calculation results of the fuel combustion parameters GT in absolute units for precise modified closed onboard helicopter's turboshaft automatic control system, fuzzy and neuro-fuzzy control, reconfigured modified closed onboard helicopter's turboshaft engine automatic control system developed in this work, respectively for given values of helicopter's turboshaft engine thermogas dynamic parameters and a step change in the required fuel combustion. The results of a comparative analysis of helicopter's turboshaft engine control task solution on the example of determining fuel consumption using various of neural networks architectures are present in table. The results of determining errors of the first and second night according to the main helicopter's turboshaft engine thermogas dynamic parameters are presented in this table. The conclusions are presented in this slide. Thank you for attention.